15th June 1941, Naval Air Station Quonset Point, Rhode Island. Lieutenant Commander Robert Seaby stood in the driving rain, staring at what was supposed to be the future of American military construction. Before him, a construction crew of 60 men struggled with a half-assembled steel structure that looked like an enormous tin can cut in half. They'd been working for 3 days, and the building still wasn't finished. 3 days for a single hut. Meanwhile, across the Atlantic, the British were erecting similar structures in just 4 hours with a crew of 6 men. The wind howled off Narragansett Bay, sending sheets of cold rain sideways across the naval station. Tools slipped from frozen hands. Bolts refused to align. The corrugated steel panels, each one heavy enough to require 2 men to lift, buckled and warped as workers tried to force them into position. Seaby watched a sailor nearly lose a finger when a panel snapped back unexpectedly, its sharp edge slicing through his work glove. This was the Quonset hut, America's answer to Britain's Nissen hut. It was supposed to be better, stronger, more modern. It was supposed to prove that American engineering could improve on anything the British had designed. But as Seaby stood there in the rain, watching his men struggle, a terrible realization settled over him. They'd made a catastrophic mistake. They'd taken a brilliant British design and somehow made it worse. Before we begin, don't forget to subscribe for more untold stories from the Second World War. Where are you watching from? And have you ever seen a Quonset or Nissen hut in person? The story begins not in America, but in the muddy trenches of the First World War. In 1916, Major Peter Norman Nissen of the Royal Engineers faced an impossible problem. The British Expeditionary Force in France desperately needed shelter, not just for troops, but for supplies, ammunition, hospitals, and command posts. Traditional wooden buildings took too long to construct, required too much lumber, and were easily destroyed by German artillery. Nissen, a Canadian-born mining engineer who joined the British Army, had an idea that seemed almost absurdly simple. What if you could create a portable building that required no foundations, no skilled labor, and could be assembled in hours instead of weeks? Working at the British Experimental Works in Richborough, Kent, Nissen designed a semicircular structure made from corrugated steel sheets mounted on a curved steel frame. The design was inspired by the shape of a barrel, structurally sound, efficient with materials, and able to shed water and snow naturally. The curved shape meant that artillery shells would often glance off rather than penetrate. The first Nissen hut was 16 feet wide, 27 feet long, and 8 feet high at the center. It weighed approximately 2,500 pounds and could be transporting on a single truck or railway car. Most remarkably, it could be erected by 6 men in 4 hours with nothing but basic hand tools, wrenches, hammers, and wooden mallets. The key to the Nissen hut's genius lay in its simplicity. The structure consisted of just a few components. Curved steel ribs, usually 9/12 per hut, made from cold-formed steel. Corrugated steel panels that bolted directly to the ribs. Timber end walls with doors and windows. Wooden floorboards laid on timber joists. Concrete or brick foundation piers, though these were optional. By 1917, Nissen huts were being manufactured by the thousands. They appeared across the Western Front, in Mesopotamia, in Egypt, and in every theater where British forces operated. By the end of the First World War, over 100,000 Nissen huts had been produced. After the war, surplus Nissen huts found civilian uses across the British Empire. They became workshops, storage buildings, temporary housing, and even churches. In the 1920s and 1930s, British engineering firms refined the design, making it even easier to assemble and more weather-resistant. By the time the Second World War began in September 1939, the Nissen hut was a proven, battle-tested design. The British knew exactly how to manufacture them, transport them, and erect them under the worst possible conditions. From the deserts of North Africa to the jungles of Burma, from the frozen wastes of Iceland to the islands of the Pacific, Nissen huts provided shelter for millions of Allied servicemen. And then the Americans decided they could do it better. When the United States began its military buildup, in 1940–1941, even before officially entering the war, the U.S. Navy faced a construction crisis of monumental proportions. The Navy was expanding at an unprecedented rate. New bases were being established from Alaska to the Caribbean. Existing facilities were being dramatically enlarged. The problem wasn't just housing for sailors, though that was critical, but also storage for supplies, repair facilities for aircraft and ships, hospitals, command centers, communications facilities, and 1,000 other necessary structures. Traditional construction methods couldn't keep pace. A standard wooden barracks building took weeks to construct, required skilled carpenters, consumed enormous quantities of lumber, and wasn't portable. If a base needed to be relocated or expanded, those buildings were essentially useless. Navy construction officers had heard about the British Nissen hut. In early 1941, a delegation from the Bureau of Yards and Docks visited British military installations to examine the design firsthand. They were impressed by the speed of construction, the minimal labor requirements, and the versatility of the structures. And this was the fatal, but they believed they could improve it. The American team, led by architects and engineers at the George A. Fuller Construction Company, identified what they saw as weaknesses in the Nissen design. The curved ribs were relatively lightweight and could buckle under heavy snow loads. The corrugated panels were thin and provided minimal insulation. The timber end walls were vulnerable to rot and termites. The assembly process, while fast, still required some skill and experience. Their solution was to redesign the hut from the ground up, using American manufacturing standards and materials. The result was the Quonset hut, named after its testing ground at Quonset Point Naval Air Station in Rhode Island. The first Quonset hut was completed in June 1941, 6 months before Pearl Harbor would bring America fully into the war. The Quonset hut looked similar to the Nissen hut. Both were semicircular steel structures, both used corrugated metal panels, but the similarities ended there. American engineers, with the best intentions, had improved nearly every aspect of the design. Structural changes. The Quonset hut used heavier-gauge steel for the ribs, 3/16-inch thick compared to the Nissen's 1/8-inch. This made the structure stronger, but also significantly heavier. A standard 20-foot-wide Quonset hut weighed approximately 4,200 pounds, nearly double the weight of a comparable Nissen hut. The corrugated steel panels were also heavier, 20-gauge steel instead of 24-gauge. Again, this improved structural strength, but added weight and complexity. Assembly system. This is where the Americans made their most significant and most problematic change. The Nissen hut used a simple bolt-and panel system. Each panel overlapped the next and was secured with just a few bolts. The joints were flexible, allowing for slight irregularities in the frame. The Quonset hut used a tongue-and-groove panel system with hidden fasteners. Each panel had to slot precisely into the next, requiring exact alignment. The engineers believed this would create a tighter seal and better weather resistance. In theory, it should have worked beautifully. In practice, it was a disaster. The tight tolerances meant that panels had to be manufactured with extreme precision. Any warping during transport, any slight misalignment of the frame, and the panels wouldn't fit. Workers had to spend hours hammering, prying, and forcing panels into position, often damaging them in the process. Foundation requirements. The British Nissen hut could be erected directly on level ground with minimal preparation. Small concrete piers at each rib location were sufficient, and in emergency situations, even these could be omitted. The American Quonset hut required a more substantial foundation, a continuous concrete sill or pier system to handle the increased weight. This added time and required concrete, which wasn't always available in forward areas. Labor and skill requirements. Here was the most damning difference. A Nissen hut could be assembled by 6 men in 4 hours with basic tools. The workers didn't need to be skilled craftsmen, just strong backs and the ability to follow simple instructions. A Quonset hut required 12 men and typically took 2 to 3 days to erect. More critically, it required workers with construction experience who understood how to read plans, align structural members precisely, and troubleshoot problems when panels didn't fit. The true test came after Pearl Harbor, when America suddenly needed thousands of buildings in dozens of locations, often in remote areas with minimal infrastructure. In February 1942, the Navy began deploying Quonset huts to newly established bases in the Pacific. The results were catastrophic. At Tongatapu in the Kingdom of Tonga, a construction battalion struggled for 2 weeks to erect a dozen Quonset huts that were supposed to serve as supply warehouses. The tropical heat warped the steel panels. The tongue and groove joints refused to align. Workers resorted to cutting and modifying panels on site, destroying the weatherproofing in the process. Meanwhile, British engineers nearby erected 20 Nissen huts in 3 days. At Adak Island, Alaska in the Aleutian Chain, American Seabees faced the opposite extreme: freezing temperatures, cons, tant wind, and permafrost that made foundation work nearly impossible. The Quonset hut's heavy weight required substantial foundations, which were almost impossible to construct in the frozen ground. The precise panel alignment required workers to remove their gloves, leading to frostbite injuries. British forces on Iceland, facing similar conditions, were housing thousands of troops in Nissen huts that had been erected on minimal foundations, with insulated liners added inside. In North Africa, following Operation Torch in November 1942, American forces discovered that Quonset huts were nearly impossible to erect in sandy desert conditions. The heavy panels sank into the sand during construction. The precise tolerances were thrown off by the unstable ground. Sand infiltrated the tongue and groove joints, preventing proper sealing. British 8th Army engineers, meanwhile, were erecting Nissen huts across Egypt and Libya with minimal difficulty, using simplified sandpad foundations. By mid-1943, the U.S. military had compiled extensive data comparing Quonset and Nissen hut construction. Construction time: Nissen hut 6 men, 46 hours average. Quonset hut 12 men, 48-72 hours average. Man-hours required: Nissen hut 2436 man-hours. Quonset hut 576-864 man-hours. Transport efficiency: Nissen hut 2,500 pounds fits on 1 truck. Quonset hut 4,200 pounds requires specialized heavy transport. Skill level required: Nissen hut unskilled labor with basic supervision. Quonset hut semi-skilled construction workers. Foundation requirements: Nissen hut minimal, can be erected on level ground. Quonset hut substantial concrete work required. Weather resistance: Nissen hut excellent, flexible joints accommodate movement. Quonset hut good when properly assembled, poor when panels misaligned. The most damning statistic came from the Pacific Theater. In 1943, American forces erected approximately 8,000 Quonset huts across the Pacific, consuming 6.9 million man-hours of construction labor. British Commonwealth forces in the same theater erected approximately 15,000 Nissen huts, consuming 540,000 man-hours. The Americans had built fewer structures while using nearly 13 times more labor. How did American engineers, working with greater resources and more advanced manufacturing capabilities, create an inferior product? The answer lies in a fundamental misunderstanding of the design requirements. The American engineers approached the Quonset hut as a permanent or semi-permanent structure. They optimized for strength, durability, and weather resistance, admirable goals for civilian construction. They assumed that construction would be performed by trained crews using proper equipment under supervised conditions. But that wasn't what the military needed. What the military needed was a temporary expedient structure that could be erected quickly by whoever was available, using whatever tools were on hand under the worst possible conditions. The Nissen hut was designed for this reality. The Quonset hut was designed for an idealized scenario that rarely existed in wartime. Major Peter Nissen had been a field engineer. He'd served in the trenches. He understood that military construction happened in mud, in darkness, under artillery fire, by exhausted men who just needed shelter now. The American engineers were civilian architects and structural engineers. They designed office buildings and warehouses. They understood codes and standards and best practices, but they'd never tried to assemble a building while being shelled by Japanese artillery. There's a brutal irony here. The Americans had access to better steel, better manufacturing equipment, better quality control. They could produce components to tighter tolerances than the British. Their manufacturing capability was vastly superior. But none of that mattered if the end product was harder to use. British engineers watched the American struggles with a mixture of sympathy and frustration. One British Army engineer, Lieutenant Colonel James Pemberton, who worked with American construction battalions in the Pacific, wrote in his diary in July 1943, "The Americans have built a hut that requires 12 men and 3 days to erect, when 6 men could erect our design in 4 hours. They've added weight we don't need, complexity we can't afford, and precision we can't maintain under field conditions. But they seem genuinely convinced that their design is superior because it meets peacetime engineering standards. They've optimized for the wrong problem." British military advisors repeatedly tried to convince American commanders to simply license-build Nissen huts using American manufacturing. The advice was politely ignored. There was national pride at stake. America couldn't be seen as simply copying a British design, especially after spending millions developing the Quonset hut. Military bureaucracy had committed to the Quonset design, ordered manufacture, ring tooling, established supply chains, and trained construction battalions. Admitting the design was flawed would require acknowledging a massive waste of resources and time, something no bureaucracy does easily. To their credit, American field engineers recognized the problems and adapted. By late 1943, construction battalions in the Pacific had developed unofficial workarounds. Simplified assembly, they ignored the tongue-and-groove system and used the Quonset panels like Nissen panels, overlapping them and bolting them directly to the frame. This destroyed the theoretical weatherproofing advantage but made assembly much faster. Reduced foundation requirements. They began erecting Quonset huts on simplified pier foundations similar to Nissen specifications, accepting that this violated the design specifications but recognizing that it was operationally necessary. Pre-assembly modifications. Stateside manufacturing facilities began pre-drilling additional bolt holes in panels and loosening manufacturing tolerances, essentially making the Quonset hut more like a Nissen hut. Hybrid construction. Some battalions combined Quonset frames with Nissen-style panels when they could obtain them through Lend-Lease supplies. By 1944, field-modified Quonset huts could be erected in approximately 12-16 hours by 8 men, still slower than a Nissen hut, but far better than the original design. The Navy eventually developed the Quonset Hut Series 40, introduced in late 1943, which incorporated many of these field modifications into the standard design. Panel tolerances were loosened, foundation requirements were reduced, assembly procedures were simplified. But even the improved Series 40 Quonset hut required roughly double the labor time of a comparable Nissen hut. Despite its flaws, the Quonset hut was produced in enormous quantities, a testament to American industrial capacity, if not engineering optimization. Between 1941 and 1946, American manufacturers produced approximately 170,000 Quonset huts in various sizes. The most common variant was the 20-foot wide by 48-foot long model, but sizes ranged from 16 feet to 100 feet wide and up to 180 feet long. For comparison, British manufacturers produced approximately 200,000 Nissen huts during the same period, despite having far less manufacturing capacity and being under constant threat of German bombing. The irony is that American industry was so productive that it could overcome the design inefficiencies through sheer volume. Yes, each Quonset hut took longer to build, but America could manufacture and ship them faster than Britain could produce Nissen huts. This masked the fundamental design problems. Commanders saw Quonset huts being deployed in large numbers and assumed the program was successful. They didn't see the thousands of man-hours being wasted, the construction delays, the field modifications being improvised. After the war, both Nissen and Quonset huts found extensive civilian use. In Britain, surplus Nissen huts became homes for thousands of families during the post-war housing shortage. They were used as farm buildings, workshops, and storage facilities. Many remained in use well into the 1980s, and a few survive today as historical structures. In America, Quonset huts became ubiquitous. Veterans returning home recognized them and found them useful for small businesses, storage, and even housing. Their distinctive shape became part of the American landscape. Interestingly, in the civilian market, the Quonset hut's disadvantages mattered less. Construction wasn't being performed under combat conditions by exhausted troops. Skilled contractors could take their time and achieve the tight tolerances the design required. The heavier construction actually became an advantage for permanent installations. Today, Quonset hut has become the generic American term for any semicircular prefabricated steel building, even though most modern versions owe more to the Nissen design than the original Quonset specifications. Let's examine exactly why the Nissen hut was functionally superior for military applications. Flexible tolerances. The Nissen hut's simple bolt and overlap panel system didn't require precise alignment. Panels could be slightly warped, frames could be marginally out of square, and the building would still go together. This was crucial in field conditions where nothing is ever perfect. Weight distribution. The lighter Nissen hut could be assembled by fewer men because individual components were manageable. 2 men could lift and position a panel. The Quonset's heavier panels required more workers, and more workers mean more coordination complexity. Foundation flexibility. The Nissen hut's lighter weight and simpler load distribution meant it could be erected on minimal foundations. In many cases, timber blocks or even sandbags were sufficient. The Quonset's greater weight and concentrated loads required proper foundations, which required time and materia. Forgiving assembly sequence. The Nissen hut could be partially assembled, left overnight, and completed later without problems. The Quonset's tongue and groove system meant that once you started panel installation, you had to complete entire sections to maintain structural integrity. Tool requirements. Nissen hut assembly required only wrenches, hammers, and wooden mallets. Quonset assembly sometimes required specialized tools for panel alignment, and often required power tools to drill out misaligned holes. While the difference between 4 hours and 3 days might seem academic in hindsight, in wartime it represented something much more significant: the difference between having shelter and not having shelter when you desperately needed it. In the Pacific Theater, where malaria and tropical diseases killed more American servicemen than combat, the speed of construction for medical facilities could be literally life or death. A Nissen hut hospital ward could be operational in days. A Quonset hut equivalent took weeks. In Alaska and the Aleutians, where exposure to the elements could kill in hours, shelter construction wasn't a logistical concern, it was a survival imperative. There's no way to calculate how many American servicemen suffered from disease, from exposure, from inadequate medical facilities, because construction took 3 days instead of 4 hours. But the number isn't zero. And there's a broader cost. Every man-hour spent struggling with misaligned Quonset panels was an hour not spent on other necessary tasks. In a war where labor was always in short supply, wasting thousands of man-hours on inefficient construction had ripple effects across the entire logistics system. The Quonset hut story offers a cautionary tale about engineering, innovation, and the dangers of trying to improve something without fully understanding why it works. The American engineers who designed the Quonset hut were intelligent, capable professionals. They applied sound engineering principles. They improved structural strength, weather resistance, and durability. By every metric that mattered in civilian construction, the Quonset hut was superior to the Nissen hut. But war doesn't care about civilian construction standards. Major Peter Nissen understood something the American engineers didn't, that the best design isn't the strongest or the most sophisticated. It's the one that works under the worst possible conditions with the least possible resources. The Nissen hut was a masterpiece of appropriate technology. It was exactly strong enough, exactly complex enough, exactly precise enough, and no more. Every aspect of its design was optimized for the actual conditions under which it would be used. The Quonset hut was over-engineered for a scenario that existed more in planning documents than in reality. This pattern repeats throughout military history. Complex weapons systems that look brilliant in testing but fail in combat. Sophisticated strategies that collapse under the chaos of battle. Impressive logistics plans that can't adapt to unexpected challenges. The side that wins isn't always the one with the best technology or the most sophisticated systems. Sometimes it's the side that understands the problem well enough to build something simple that just works. Today, both Nissen and Quonset huts have faded from military use, replaced by modern containerized housing and rapidly deployable shelter systems. But the fundamental lesson remains relevant. Major Peter Nissen, working in a British experimental facility in 1916, created something that American engineers in 1941, with vastly greater resources and more advanced technology, couldn't improve upon. Not because the Americans lacked skill or knowledge, but because they optimized for the wrong problem. War is the ultimate test of engineering. It strips away all pretense, all theoretical advantage, all concern for how something looks on paper. In war, the only question that matters is, does it work when everything is going wrong? The Nissen hut worked. The Quonset hut eventually worked, after extensive field modifications essentially made it more like a Nissen hut. There's no shame in copying a good design. There's no virtue in reinventing something that already works. Sometimes the most innovative thing you can do is recognize brilliance and simply replicate it. The British had created something perfect for its purpose. The Americans, with the best of intentions and the full force of their industrial might, tried to improve it and instead made it worse. It's a reminder that in engineering, as in life, more isn't always better. Stronger isn't always superior. And sometimes the smartest thing you can build is something beautifully, elegantly simple. But in the frozen North Atlantic, another battle of engineering and will was playing out, a battle where British innovation would once again prove decisive. Join us next time as we uncover the story of how Britain's acoustic sea torpedoes turned the tide against the U-boat menace, and why Germany's counterweapon came too late to matter. Don't forget to subscribe. The best stories of World War II are the ones that show us how simple brilliance defeats complex failure.